We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Okay, good morning. So Vedant, can you hear me?
Hi, sir. Samraj.
Hello Vedant.
Yes, sir.
Okay, so shall we start?
Okay.
Okay, so distillation column design. This is a very important topic as far as equipment design is concerned, as well as you are learning mass transfer operations. So there also you are learning distillation column operations at least. And in industry also, distillation is a very important unit operation in the chemical industry, and that's why it's very interesting and very important one also to learn this aspect. So what do you mean by distillation? That's a basic definition you learn to some extent in your master's for operations. So basically we mean distillation is nothing but the separation of a okay. So distillation, sorry, there is some technical reason, something. So distillation column, distillation is a separation of two liquids or more than two homogeneous liquids using a difference of boiling point or a vapor pressure difference. That's what we are saying is separation of a liquid mixture based on either the boiling point difference or based on the difference of the vapor pressures. Uh, uh, what is the important aspects we need to learn in a distillation column? Ultimately, after design, what you are going to given as output. So after completion of a distillation column, you are going to have a complete sizing. We have defined that design is nothing but the sizing, and sizing means we need to determine the number of trays. For example, basically broadly we can say it's the height and diameter of the column, including all the parameters, where the height includes your number of trays or height of packing, diameter, flow rate, etc. All the aspects we need to consider as a final design. We need to give as an output of a final design. And so as output of distillation, we need to give final height and diameter, the number of trays, flow rate, temperature, pressure, we need to determine. Fine, so you have learned something basics in MTU operations, masters of operations, that which are the various methods to design a distillation column. So broadly for a binary distillation column, you learn that you have a McCabe-Thill method and Ponchon-Severith method. So McCabe-Thill method is used very broadly, very largely, but under some specific conditions. You are making certain assumptions to design a distillation using a McCabe-Thill method. Fine, are you? So which are that assumptions? One of the most important assumption is that the relative volatility, when you are considering that latent of vaporization is remain almost constant, and that's why we are assuming that if on each and every tray of a column you are considering a constant molar overflow. What do you mean by this assumption of constant molar overflow? Fine. So it means that if we consider the liquid flow rate in a distillation column, column is designed in two sections. Fine. Above the feed is considered as a enriching section, and below the feed is known as a stripping section. Fine. So both, there are two different sections comes in a picture. So in each section, if I consider that, for example, tray number 1 from in the top above the feed, that is the liquid fluid L1, L2, L3, like that. So if I assume that constant molar overflow, what it means that liquid flow rate, the flow rate of liquid on a tray 1, liquid fluid on the tray 2, or liquid fluid on tray 3 up to the feed tray, that is remain constant. Number of moles, kilomole per hour flow rate of liquid on each tray is remain constant. Same is the case with the vapor. So maybe V1, V2, V3 is also going to be remain constant. That is what is meant by the constant molar. Well, same thing we apply for the stripping section below the feed. Definitely above the feed and below the feed, your liquid and vapor flow rates may be different, but definitely in that particular section is remain constant. So this is one of the most important assumption, and that assumption is validated on which basis? How the liquid molar overflow remain constant? We can say that it is only based on The one more important assumption you're considering, that is the latent heat of vaporization. If you remember, if you go through that assumptions given in a McCarthy method in a MTO book, then you can see that I can assume constant L1, L2, L3 only in one conditions, because on each and every tray there is a transfer of molecules. Fine, mass transfer is taking place, concentration is changing, but still your molar flow rate, kilomole per hour, remains constant. So under which circumstances it is possible that it is only possible that number of moles evaporated from the liquid to vapor, same number of moles must be condensed from vapor to liquid. Fine, then and only then your liquid flow rate remain constant in a stripping section or enriching section. And same is the case with the vapor flow rate remain constant either in the stripping section or enriching section only and only when there is a same number of moles transferred from vapor to liquid phase and liquid to vapor phase. But when it is possible, that is only possible when the latent heat of vaporization is remain constant. Are you agreed? Are you sure that it is possible to maintain constant molar overflow with a different or a large variation in the latent heat of vaporization? Fine. So that is the reason that when the latent heat of vaporization changes largely across the column, fine, component A in the top is a pure component and component B in the bottom. So throughout, for all the trays from top to bottom, if this latent heat of vaporization changes significantly, then we cannot keep all the liquid or vapor fluid constant, and that's why in that situation we must have to go for the punch on separate method. That is one of the important assumptions which you are making. Fine, hopefully you have learned in the MP operations. I'm not going into detail in that aspects. Now when you start designing, maybe by the McCaffrey method, maybe we have punch on separate method, or any other method which we are going to learn, like a shortcut methods. Fine, uh, Fensky underwood Galilean equation base, we are going to learn shortcut method in this particular chapter, distillation design. So whatever the method you use, you have to determine all the parameters, design parameters. Fine. So according to that, the first aspect comes in a picture. Fine. I have mentioned a few questions over here, but which normally I'm asking that in even a pack column design, we have learned that when you start designing either for absorption column or distillation column, the first question comes whether you want to go for the pack column or a tray column. Fine. So we have learned the advantages and disadvantages and selection criteria for the pack column. Can you suggest similarly the tray column selection, under which circumstances you may recommend to go for the tray column? So normally we are saying that whenever the pressure drop requirement is the lesser, fine, very stringent requirement is that we recommend to go for the pack column. Otherwise, definitely we can go for a tray column where, fine, when you are operating above the atmospheric pressure, when the pressure variations is very large, fine, in that situation we can go for the tray column. And when the operation quantity is very large, we normally recommend to go for the tray column design. Fine. So once you selected, yes, we are going to design a distillation or absorption column by a tray, using a tray. Then next things comes in a picture. What are the temperature and pressure is going to be? How we can select the temperature, pressure of the distillation operation? Fine. Can you suggest that how we are going to determine? All of you must have come across the various column operations of under different pressures. So under maybe CPI under CPI as a subject, chemical process industries, or some other subjects. When you come across that distillation column can be operated, fine, we have three options. Which are they? Pressure inside the column can be equal to 1 atmospheric pressure, means like atmospheric pressure, or it can be a greater than 1 above atmospheric pressures, or it can be a below less than 1 atmospheric pressure. So we can say that either it is a vacuum operations or atmospheric operations, or at a high pressure operations comes in a picture. Fine. And industry, all the three pressures are is under operations. Fine. So under which circumstances you may select the suitable pressure, and definitely temperature will be according to the pressure. Fine. Because inside the distillation column, if you look at it, the T versus XY diagram in a distillation in your TXY diagram, then you can come to know that your distillation column is separation is only possible in a distillation when you operate in a binary phase. Fine, means that within the distillation column, your two phase must exist. Must means you cannot carry out the separation. Like if you remember TXY diagram, then you cannot have a separation only in a vapor phase, only or in a liquid phase. Fine. So if you want to carry out a distillation operation, you must have to have a existence of vapor as well as liquid, and that's why your TXY diagram where both the overlaps comes in a contact with each other, that is in between phases, in between portion of the two overlaps, close loop is indicating the region of operation of a distillation. So distillation is nothing but we need to have a presence of both vapor as well as liquid at that temperature and pressure condition. So once you fix the pressure, automatically temperature will be defined. If you remember that within the distillation column, all the time we are operating under the between the two saturation points. So from liquid saturation to vapor saturation. So within the distillation column, if you look at it, our none of the liquid is going to be subcooled, or our all the vapors are going to be means none of the vapor is going to be superheated. So all the liquid which are there inside the distillation column, they are all a saturated liquid, and all the vapor molecules which are there in the distillation column are only saturated vapor. So what do you mean by saturated liquid is a bubble point, and what is the saturated vapor is a dew point. So we are going to operate our distillation column within the range of from bubble point to dew point. Definitely now both the ends at the top and bottom of a distillation column, so they ultimately they are the pure products. Top at the means low boiling point component A, and B is the bottom product, is a high boiling component. But ultimately at the top and bottom, ultimately they becomes your boiling point of the respective components in its pure state, if we are getting a pure product at the top and bottom. Fine. So ultimately the operation of the distillation column, the temperature range will be decided. It's simply it's the boiling points of the two components, but at which pressure. So definitely boiling point varies with reference to pressure, and that's why the as once you fix up the pressure, your corresponding temperature will be fixed up, and that's why it is very important to fix the operating pressure of a distillation column. So I'll just mention that operating ranges, it may be a atmospheric pressure, it may be a vacuum, or it may be high pressure. So how we can choose, how we can select the pressure? So to some extent we have learned in a pack column that whenever the I have if boiling point now here the operation is not only decided based on the feasibility of the distillation. Apart from the distillation, we need to check out the other possibilities. Definitely, first aspect, for example, let me give an example. If I want to carry out a separation of air, fine, yes, we have a pure oxygen and pure nitrogen requirement is there, and at a large scale distillation is a recommended operation for a separation of air, means separation of nitrogen and oxygen from air. Fine. So in that situation, can you carry out a distillation operation at a 1 atmospheric pressure? Is it possible? No, it is not possible, because at a 1 atmospheric pressure, fine, it is definitely means you require a temperature. If I want to liquefy, I want to have both vapor and liquid coexist, then definitely the temperature range is my boiling point of the nitrogen is minus 290 something, which is very difficult and economically is not viable to have that such a low temperature. Fine. So in this situation, so what we recommend, so in that case, how I can increase the boiling points of the nitrogen and oxygen. So in that situation, it is easy that let me increase the pressure. So fine, if I increase the pressure from 1 atmospheric to maybe 100 bar, maybe 50 bar, 100 bar, and you check it out how the boiling point is changing, and that's how we are going to choose separation of nitrogen and oxygen from air at a higher pressure as well as low temperature definitely comes in a picture. Fine. So here we choose to operate at a above than a 1 atmospheric pressure. Reason only that it is easier to reduce the temperature at maybe 100 bar pressure. The boiling point of the nitrogen and oxygen may be somewhere minus 80, minus 90 or something like that. So which is much easier to achieve using the suitable refrigerant rather than to achieve minus 290 degrees centigrade. Fine. So this is how. So similarly, if you want to have a separation of some such components which are remain in a vapor phase at a atmospheric condition, in that situation you simply recommend that increase the pressure of the column and convert it into the increase the boiling point so that you can choose its range which is feasible and economically viable. Fine. Second case, when you can go for the, when you recommend for the vacuum, fine. So like heat sensitive materials, when you operate for some heat sensitive like fruit juices, fruits, medicines, or some other components which are going to be get degrade when we expose for a high temperature, fine, like a crude oil distillation, whatever we are petrol, diesel, we are getting it, that is coming from the refinery. So refinery operations, it involves atmospheric distillation unit as well as vacuum distillation unit. So whatever the product comes from atmospheric, bottom product of the atmospheric distillation unit, they reach to such a composition where its boiling point reaches almost 340, 350, more than 350, 400 degrees centigrade. So if you continue to boil such a heavy crude fraction at a 350 or 400 degrees, it's a degradation starts. Fine. So it is not recommended to heat it at such a high temperature. So in that situation, we recommend to go for the vacuum distillation and vacuum operations where I can reduce the pressure. If I reduce the pressure, now boiling point is also reduced, and that's why I can separate out. Similarly, for example, if I have some medicine which gets degraded at 80 degrees and 80 degrees centigrade, I cannot boil it. I cannot boil that compound at 80 degree centigrade. So what I need to do? So let us we carry out the same, because I need to have a separation. So in that case, I can carry out the separation of it using a distillation at a lower pressure, maybe under vacuum, so that its boiling point may be reduced. And so instead of 80, I can boil it maybe at 60, and I can carry out a separation. So that's how the selection of a pressure comes in the picture. We need to check its feasibility, and we propose a pressure according to the requirement. If both the vapor and liquid coexist at 1 atmosphere, and then is the best choice, because increasing high pressure or decreasing and converting the vacuum both requires some monetary aspects, some finance is required. So we recommend to go for the, if possible, 1 atmosphere pressure is without any other extra cost involvement. Fine. Yes. So this is based on the nature of the components which are involved in the separation. But many a times it happens that we recommend that not only the component nature, but other operations affects the even distillation column temperature pressure. How it, for example, you have a top product component A which has a boiling point of only 35 degrees centigrade. Fine. So what happens if you want to design a distillation column at a 1 atmospheric pressure? In that situation, what is going to happen? Now the boiling point is only 35 degrees centigrade. So which coolant you are going to use at the top of the distillation column? So you remember that a distillation column involves condenser design, condenser at the top and reboiler in the bottom. So now as a condenser, when you have to condense the vapor and you have to convert it into liquid, so only 35 degrees is the boiling point of the component. Fine. And if you are designing a distillation column in a country like India or even a city like Ahmedabad, what is going to happen in a summer season? Are you able to operate properly your condenser in the situation? Because in the summer situation, summer conditions, Ahmedabad temperature goes almost up to 45 degrees centigrade. Fine. So can you achieve, what is the coolant which you are going to recommend for this situation? Can you use the cooling water as a suitable cooling coolant? Fine. So if you choose water as a coolant media, then how you can achieve, fine, sufficient delta T required to design a heat exchanger? Fine. We are saying that, and again your delta T depends on the capacity. Like I can increase the temperature, like you can say that yes, if I go for use of a cooling water, your 35 degrees centigrade is a vapor temperature, when it gets condensed at 35 degrees centigrade. So what will be the water temperature maximum you can have it? Normally we are recommending that delta T LMTD, delta T MTD at any circumstances should not be less than 10 to 15 degrees centigrade. Fine. So if you go for the water temperature, fine, maybe ranging from maybe 20 to 20 to 30 degrees centigrade. Is it possible? Can you achieve this range of 20 to 30 degrees centigrade of inlet outlet water? Fine. Even you design from 25 to 30, is it possible? Because your wet bulb temperature itself in a summer season in Ahmedabad is hardly going to be 28, 29 or 30 maybe even. So that's why you are going to face a lots of problem in operation of a distillation column in terms of your improper condenser. Condenser cannot take a load of a vapor, and that's why you're not able to get the required uh, liquefaction. So in that situation, what is going to happen if you replace water? Now as a design, if you choose to use some refrigerant, yes, you can always do that. You can use some refrigerant where you can or means like ice water and brine. Okay, so sorry, there are some technical connection issues are there. Can you hear me? Okay, so we need to determine the pressure. So in that sense, we can determine. So when your coolant is a chilled water, where its temperature ranges from 5 to 10 degrees centigrade, for example, you can use sufficiently fine, but cost of such coolant is going to be much higher compared to the cost of cooling water. So in that, what is the recommended? What is the more economical? Instead of using a chilled water, can I use same cooling water, normal cooling water as a coolant, and by increasing the pressure of the distillation column, fine. So instead of 1 atmospheric column, if I choose to operate at maybe 5 or 10 atmospheric pressure, fine, 10 bar pressure. So now the boiling point, which was maybe earlier 35 degrees centigrade, becomes maybe 60, 50, 60 degrees centigrade. And now I can have sufficient delta LMTD or MTD in the heat exchanger, and I can use the same cooling water as a coolant media inside the heat exchanger. And so that's how the operation of the distillation column can be decided. Fine. So that's how we decided the pressure and the corresponding temperature based on its bubble point and dew point can be fixed up, and it will be fixed automatically. So what are they looking from the distillation, or what is the outcome? I decided the design, the sizing comes out. Height. So ultimately we have to determine the height and diameter of the column. Fine. This question's fine. It's coming in a picture. We'll discuss one by one. Okay. So now this is very interesting one. We have learned again this aspect in a pack column also. Fine. Specifically, definitely all the column operations when we design, it must make sure that there should not be, it must work sufficiently, it must produce the desired product. Fine. So I'm normally saying these are the boundary conditions. We are in a pack column also, we have fixed our maximum flooding velocity, and according to that our design was considered. Fine. So it also the all the columns are designed based, it's a vapor velocity is based on the flooding velocity on the higher side, definitely. But on lower side also, like you have the various operation, various concerns comes in a picture. So that is various what I should say, okay, irregularities generate Taichi column, that is conning, whipping, excessive entrainment, down comma backup, and flooding. These are the boundaries, boundary conditions share column. We have to operate. I'm normally saying it is a line of control. Fine. You must have to make sure that કે તમારું જે operation થાય તે અહીંયા satisfactory area માં within the boundary or LOC ની અંદર જ થવું જોઈએ. જેને cross કરવાનો પ્રયત્ન કરશો તો your design will fail. So operation will fail and you cannot get a desired product as our output. So as like you are starting with if you have a very low rate of vapor, so what is the whipping and what is the dumping? Fine. So when you have a very low rate of vapor and you increase this liquid flow rate, what happens? Whipping is going to start. Whipping means what? Like normally we are saying whipping is a crying. Fine. So column also cries. So what happens in a tray column? For example, sieve tray is there. So your liquid is moving on the tray. Fine. And vapor is coming through the holes. So there is no sufficient pressure in a hole of a vapor, means vapor which does not provide a sufficient. Okay, so we are getting a timeout. So in next 10 minutes it will be over. Definitely we'll continue in the evening session of 4 p.m. So let's continue for next 10 minutes. So whipping is nothing but because of low vapor pressure, vapor does not have sufficient pressure. So what happens? Liquid will come out from the holes of the sieve, fine, and that's why it is known as a whipping. But if your vapor flow rate is significantly low, fine, so what happens? Liquid, none of the liquid goes to the downcomer, up to downcomer, and all the liquid will come out from the holes, and that is known as a dumping, fine. So dumping, whipping, your conning is now, instead of liquid flow rate, if I increase the vapor flow rate, so what is going to happen? So you just try to imagine that you have some jet of like compressor air inlet you have, and you put it in a bucket of liquid. So what is going to happen when you start a compressor air? It will come out as a jet, fine. So similar things happens when you have a liquid pool on the tray. From the bottom, your vapor is coming, fine. Vapor is coming from the bottom. So if its pressure is very high, ideally what should happen? When the vapor comes out from the solid wall of the tray, it make a small bubble when it enters in the liquid pool, and that small bubble rises, and that's how the contact between the vapor and liquid takes place, and mass transfer is going to take place. But if the vapor pressure of the vapor is very high, vapor is coming with high like a jet pressure, it will try to displace the water, fine. એ શું કરશે? વોટરમાં એક જગ્યા કરીને સીધી બહાર નીકળી જશે, and that's why the contact between the vapor and liquid is not going to be there, fine. So that is known as a conning on the HA. Still, if you increase the vapor flow rate, then it reaches to the entrainment region. Entrainment એટલે carry over કરી શકે છે, just vapor તમારું liquid સાથે લેતું જાય છે. That is not a separation, it is carry over, and that's why it should not occur. And on the another side, when liquid fluid increases much higher than liquid backup, downcomer backup છે, ત્યાં તમારો liquid નો ભરાવો વધતો જાય. The accumulation of liquid increases downcomer backup, which is also not good. And both at extremely very high liquid and vapor flow rates, ultimately flooding occurs. So flooding is from name itself. What it indicates? That જેમ પૂર આવે, flooding is nothing but પૂર. જેમ આપણે સિટીમાં વરસાદ પડે અને પૂર આવે, so like that column is flooded. Flooded means that is all the volume is occupied by the liquid, right? Which is not good. Absolutely no change in the concentration from top to bottom. So that's why it is the worst condition, and that should not occur ever. And that's we must have to be most careful. If once column flooded, you have to stop you have to shut down practically everything. You have to remove it, and then you have to restart the column after removing all the things. And so it takes a lot of time, so we have to be very careful. So our design operation must take care that our design parameters must contain check for all these parameters, and definitely we are going to have flooding velocities, whipping conditions, and we are going to hand down backup limitations as our checkpoints are there. Find these interesting aspects definitely. So multi-stage operation, binary distillation column, which you will learn to some extent, McCabe method and Ponchon Surrey method. McCabe is applied only for some limited conditions where your latent of vaporization, latent lambda value change is limited for both the two components or throughout the column. And whereas Ponchon Surrey, whenever there is a temperature variations, then when we cannot maintain the constant Muller overflow condition, we have to go for the Ponchon Surrey method. Fine. Definitely, we are not going to learn in this PED. You have learned to some extent in your MP operations. So please continue that. We are going to have now multi-component distillation column design, that is, and shortcut method only. There are rigorous methods also. Even in semester 8, your multi-component design MCD, you have one special course where you are going to learn the same thing. But let us learn in this very interesting one, just an overview. So all of multi-component, what do you mean by multi-component? So whenever more than 2 components comes in a picture, fine, more than 2 components, maybe definitely 3, 4, 5, 6, whatever are there, then you can use this method. Shortcut again means we have to use shortcut from name itself means it is not a rigorous method. We are not going to have all the parameters, but some basic parameters we can identify, we can calculate in a very simple way. Fine. So now all of you learn the Fensky equation, if you remember, in MPO again. So this is the same Fensky equation, we arrange it in this manner It gives us the minimum number of stages required. Fine. Minimum number of stages required with this formula or correlation. So now very interesting aspect is that this LK and HK two terminology comes in a picture. Light key and heavy key. What is that light key and heavy key? Fine. So now we have to define. So this is the most important aspect when you are going to design a distillation column using a Fensky underwood Gilliland equation or shortcut method of FUG method. Fine. So if you make a mistake in this key component definition, then definitely your whole calculation may go wrong. So according to that, what is this LK and HK? LK is a light key component which should kept out of the bottom product. Fine. LK should be in traces of in bottom and major fraction should be recovered in the top product. And HK is heavy key component which should be kept out of the top product. HK should be in traces in the top product and major fraction in the bottom product. Now, for example, we have a benzene, toluene, and xylene. For example, this is the ternary mixture. Three components are present in this. So now if I choose, like I need to carry out a separation of benzene from toluene, right? I repeat, we have benzene, toluene and xylene in increasing order of their boiling point. So benzene is the lightest, toluene is intermediate, and xylene is the highest boiling compound. So now if I want to separate benzene and toluene, so in that situation, I need to remove benzene completely at the top. Fine. I'm saying that I want to separate benzene from toluene. Fine. So I need to recover benzene in the top and toluene in the bottom. Fine. So in that situation, what happens? Your light key, fine, is becoming benzene, and alkane should be traces in a bottom product. Like only very small fraction, maybe 1% or less than that. Only small fraction of benzene should be observed or collected in the bottom. Definitely, we cannot 100% removal. You cannot say in a distillation that you can achieve a 100% purity. It is you can say it is 99.999, but you cannot say it is 100%. It's not possible. Fine. So that's why we are saying that your light key may be very small fraction in a bottom product. So benzene all must be recovered in the top product, and very small amount may be there in the bottom product. Fine. And similarly, your toluene, benzene and toluene. So toluene is in the bottom product, that becomes a heavy key, and only small fraction maybe gets with the benzene. It is only in the top product. So major fraction of heavy key is in the bottom product. So toluene and xylene you can observe in the bottom product, whereas benzene is only in the top product. But I say that I need a separation between the toluene and xylene. Fine, now I'm changing it. So in that situation, what is going to happen? Now your
Sorry, Mike. Nah, nah.
toluene is now we want to separation of toluene and xylene. In that situation, what will happen? So we are going to define now toluene as a light key. So we need between toluene and xylene. Fine. So we are going to get benzene and toluene in the top product, and only xylene in the bottom product. Very small fraction of toluene will be there in the bottom, and very small fraction of xylene will be in the top product. Fine. So that's how